Hello, I'm Zihao from East China Normal University. Here, I am happy to introduce you our work, Hybrid Evaluation for Distributed Iterative Matrix Computation. The whole point of this work is to exploit both full and incremental evaluation to accelerate execution of distributed matrix computation solutions. This presentation consists of 6 parts. I will start with the motivations of using hybrid evaluation in matrix computation. And then parts 2, 3, and 4 will introduce the main ideas of our work. Part 5 will introduce the architecture of our system, and at the end, I will present the experimental results demonstrate our contributions. First, let me introduce our application scenarios. Matrix computation is pervasive in numbers of fields, such as machine learning and statistical science. In particular, we focus on a common type of matrix computation workload, which is iterative algorithms. Examples are network centrality analysis, matrix factorization, and regression analysis. For this algorithm, there are 2 common features motivate our work. First, we observe that elements gradually converge at different rates, which motivates us to use incremental evaluation. Second, incremental evaluation itself incurs extra overhead, which motivates us to use hybrid evaluation to further improve the performance. Next, I will explain these features respectively. In specific, during an iterative process, the update elements typically converge at different rates. That is, we may recompute those elements with early convergence. Here I give an example of PageRank on a 6-node network. The first line here shows the iterative expression of PageRank. And after 19 iterations, we notice that the ranks of node 2 to node 6 have already converged. However, the original full evaluation repeats computation on these ranks, regardless of the redundancy. Here, the redundancy is circled by red boxes in this figure. This motivates us to adopt the idea of incremental evaluation to avoid such redundancy. Here I give the expression of incremental evaluation for PageRank, where delta R represents the increment term in PageRank. And at the 19th iteration, delta R contains only one non-zero element, which is delta R1. So, with incremental evaluation, we can simply transform the original matrix vector multiplication GR into a vector scalar multiplication G1 delta R1, and therefore accelerate the execution. The second common feature is that incremental evaluation incurs extra overhead, such as the computation of increments and the addition to increment term. Here I present the performance of full and incremental evaluation at certain iterations of PageRank and the matrix factorization algorithm, which is GNMF. As you can see, after running a few iterations, incremental evaluation managed to outperform full evaluation. For example, at the 8th iteration of PageRank and the 26th iterations of GNMF. However, at the 2nd iteration of PageRank and the 7th iteration of GNMF, incremental evaluation is clearly slower than full evaluation. To further examine the extra overhead of incremental evaluation, we conduct an experiment on an iterative expression x equals ax. And as the column number of x increases, the extra overhead, which is indicated by the yellow area in this figure, becomes overwhelming. As a result, we conclude that we cannot simply use incremental evaluation to improve performance all the time. This motivates us to propose hybrid evaluation, which dynamically chooses full or incremental evaluation for each iteration, so as to fully utilize both of their advantages. Following this idea, we design hybrid plan, which interleave full and incremental plans. This figure depicts its execution procedure. For each iteration, a hybrid plan first compares the cost of full and incremental plans, and then conducts an iteration under the optimal plan. In this procedure, we also notice two issues limiting the performance improvement. First, for incremental evaluation, the sparse updates hinder the effect of optimizing network communications. And second, for hybrid evaluation, the comparisons incur extra overheads that offset the performance improvement. So next, I will discuss these two issues and explain our corresponding optimizations respectively. First, in distributed environments, a large matrix is sliced into multiple blocks, and the sparse updates here mean that there are incremental updates scattered across the blocks. For illustration, let's go through the process of the product AX and A delta X respectively. Here, matrix A is sliced into 4 blocks, and matrix X is sliced into 2 blocks. A common method computes AX in 3 steps. First, it broadcasts the small matrix X so that each node of the cluster can access X. Second, it multiplies the corresponding blocks of A and X to provide the intermediate results of the product. Then, it aggregates these intermediates via a shuffle so as to obtain the final product. Among these 3 steps, the shuffle here is a bottleneck due to its overwhelming communication costs. Next, let's see the product A delta X. Clearly, the incremental evaluation managed to reduce the costs of broadcast and multiplication. However, in general, the incremental updates scatter across blocks. That leads to no reduction to the cost of the shuffle. As a result, incremental evaluation fails to address the performance bottleneck and therefore has limited effect on the performance improvement. Our optimization is to reorganize matrix to gather incremental updates into as few blocks as possible before computing the product. Here, we permute the rows of delta X and the columns of A accordingly. If the matrix A is partitioned into rows, as shown in figure A, we perform column-oriented reorganization. That is, A and delta X are permuted within partitions. Otherwise, if a matrix A is partitioned in columns, we perform row-oriented reorganization, which means permuting A and delta X across partitions. Clearly, this reorganization incurs extra communication costs as well. So in case our optimization reduces the performance instead, we use a cost model to determine whether to use matrix reorganization. Note that the matrix reorganization does not affect the computation results according to the property of matrix permutation. Consequently, we can reduce the cost of the shuffle in the multiplication process. In this example, we can even avoid the shuffle, since we gather the increments into one block, and therefore exploit the benefits of incremental evaluation. The second issue is about the comparisons in hybrid plans. To explain this, I first introduce the comparisons used in our system, which is based on cost evaluation. Here, I illustrate the cost of full and incremental evaluation for PageRank. The cost here is calculated by evaluating and accumulating the costs of each operator. Clearly, among these operators, the cost of two multiplications, GR and G delta R, are critical to the comparison results. Therefore, the statistics of delta R are essential for us to acquire accurate comparison results. In addition, we have to extract the increment term delta R first to obtain these statistics, which is costly. So considering these 2 points, if we want accurate comparison results, then the extra overheads of comparisons inevitably occur and offsets the performance improvement. We intend to reduce comparison times to address this issue. The idea comes from 2 observations. First, if a comparison result is to use full evaluation, then the comparison is consequently detrimental to the performance. Second, in general, incremental evaluation is slower than full evaluation at the beginning and gradually outperforms full evaluation after multiple iterations. Based on these 2 observations, we propose a selective comparison strategy. Since incremental evaluation is slower at the beginning, a hybrid plan starts with a long comparison step to avoid unnecessary and frequent comparisons. However, a long step also means missed opportunities in utilizing incremental evaluation. To overcome this side effect, a hybrid plan dynamically adjusts comparison steps based on historical evaluation results obtained in previous iterations. If the historical results show that incremental evaluation is now close to or even faster than full evaluation, then the hybrid plan will decrease the comparison step. In specific, we use the evaluate costs, including the cost of incremental plans, comparisons, and full plans to compute lambda. The lambda here is used to evaluate the worthiness of a comparison. A comparison is worthwhile when lambda equals 0 and becomes less worthwhile as lambda increases. Then, we use the function u lambda to estimate the proper comparison step. Clearly, since lambda equals 0, meaning it is worthy to perform a comparison, u lambda should be 1 when lambda is 0. And as lambda increases, u lambda should become larger because a comparison is more likely unworthy in this case. We have tried 4 types of u lambda, including linear, concave, convex, and conservative estimates. According to our experiments, all of them managed to estimate comparison steps properly. As a result, the selective comparison strategy saves unnecessary and frequent comparisons, and therefore improves the performance. Following the ideas and optimizations mentioned above, we implement a system called HiMac, and this figure depicts its architecture. The architecture consists of a compiler, an optimizer, and a runtime component. First, Given a user program, the compiler parses it to extract a full plan and translates the full plan to an incremental plan, and then combine these two plans into a hybrid plan. Then, the optimizer takes the execution plans, optimize them, and feeds them to the runtime component. Here, for the incremental plan, the optimizer employs matrix reorganization to reduce the communication costs. And for a hybrid plan, the optimizer also applies selective comparison strategy to either choose the full or incremental plan. Both matrix reorganization and selective comparison strategy depend on the cost model. And finally, the runtime components execute the optimized plan. Next, I will show you our experimental results. Here is our experimental setup. We conducted experiments on a 7-node cluster. Each node has two 6-core processors, 32 GB DRAM, a 4 TB hard disk, and 1 gigabit per second Ethernet. We chose 4 algorithms with distinct characteristics, including PageRank, hyperlink-induced topic search, alternating list squares, and Gaussian non-negative matrix factorization. And in our experiments, we used 6 datasets as listed in this table. There are 2 small datasets with less than 100 footprints, and 4 large datasets which require over 30 GB footprint each. First, we evaluate the performance of full, incremental, and hybrid plans. On average, hybrid plans are 1.3 times faster than full plans. For PageRank and hits, since the extra overhead associated with incremental evaluation is negligible, the performance of hybrid plans and incremental plans are comparable. But for the other algorithms, ALS and GNMF, hybrid plans are 1.2 times faster than incremental plans. We also conducted experiments to demonstrate the effect of our optimizations. In Figure A, green bar and the blue bar represent incremental plans with and without matrix reorganization, respectively. On average, matrix reorganization managed to reduce around 20% remote data rate. In Figure B, the first 2 bars are hybrid plans with fixed comparison steps. The last bar is with random comparison steps, and the other 4 bars are our selective comparison strategy with different function u lambda. As you can see, the selective comparison strategy improved the performance by around 10% in comparison to the fixed comparison steps and random comparison steps, and the different types of u lambda achieve comparable performance. At the end, we conducted experiments to evaluate our hybrid plan in comparison to alternative solutions, including our full plans, SystemL, ScienceDB, and ScalaPack. On small datasets, the hybrid plan is 2 times faster than the full plan and SystemL, and more than 8 times faster than ScienceDB and ScalaPack. And on the large datasets of 30 GB, the hybrid plan outperforms the full plan by 23% and achieves the speed up of 8 times over SystemL. Thanks for your attention.